Connor, I got yours. Thank you. Jack, I got yours. Thank you. Okay, everybody should be finishing up and get that sent off to me. I'm going to wait for just a minute for everybody to send those in so we have them. Lucille, I have yours. Give you about another half a minute to get that sent in. Just waiting on Arushi and Jordan.
I'm trying to use that Genius app, but it won't let me send it by email.
Can you just shoot a picture with your phone and then send that?
Yeah, I can do that.
Yeah, go ahead and try that. Same thing with you, Arushi, if you're having problems with the Genius scan. Just shoot a good, fairly clear picture on your phone and then send that to me as attachment. Okay, got your post in the chat, Arushi.
All right, I sent it by email.
Perfect. I'll let you know as soon as I receive it. Okay, Jordan, I got yours. I don't see an attachment on this, but maybe it's in the body of the email. Yep, it's in the body of the email. Beautiful. You're good. Excellent. Okay, Rishi, just waiting on yours. Okay, so we'll come back to this, and I'll run through the solution. But let's continue the work that we were doing in our lecture on Friday last week. So let's I'm going to leave some space here, and that should be about enough space there. So we're just going to pick up. So this is a continuation of the analysis of our circuit. Okay, so when we left in the middle, we had two nodal equations, and I'm going to go to my notes and give you the two that I have here in my notes. They may or may not be exactly in the same form, but it should look something like this. 2 plus 3j times v1 minus 2v2 is equal to 8j. That was the first equation. And the second equation was minus 2v1 plus 2 plus 3j v2 equals minus 2j. Let me know if you have anything different than those two. Okay, so we established the last time that we knew we were solving for the voltage V. The voltage V was across the resistor, right in that middle branch. There's a 1 ohm resistor, so we were looking for the voltage V. And we said V was equal to V1 minus V2. That was our V. So unfortunately, that means over here in these equations, we have to solve for both V1 and V2. So let's go ahead and do that. Now, this is where you talk about substitution and elimination and all those things not working really well. This is where Cramer's rule comes into play and is really, really much easier than using elimination methods. So we're just going to solve for V1 and we're going to solve for V2. Let's start with V1. V1 is equal to, yeah, the math was with complex numbers, but big deal. So the denominator, 2 plus 3j minus 2 minus 2, 2 plus 3j. In the numerator, we have 8j minus 2j minus 2, and then 2 plus 3j. Okay, so this is, spell it out, 8j times 2 plus 3j minus cancels, minus 4j, all divided by, it's going to be 2 plus 3j squared, but I'm going to write it this way so we can FOIL it, minus 4. So let's see, 8j times 2 is 16j, 8j times 3j is minus 24, minus 4j. In the numerator, in the denominator, I have a 4. For the real parts, I have a 4, and then I have minus 9. Minus 9 comes from the 3j times the 3j. And then I have 2 times 3j, and then 2 times 3j. So I double that, and I'm going to end up with 12j plus 12j. A little cleanup now. So just writing it in the correct order, minus 24 plus 12j divided by minus 5 plus 12j. So hopefully I've done all of that correctly. I'm not sure that I have. But assuming that I've done that correctly, I know that my denominator, just double check, 2 to 4, 4 minus 9, plus 12, 12j. Okay, so it looks good. So I know for V2, this is the beauty of this. V2, we know the denominator is going to be the same, minus 5 plus 12j. So the numerator this time is 2 plus 3j minus 2. And then on this side over here, this is where I put my 8j and my minus 2j. I made a mistake somewhere. Did I make a mistake somewhere? No, that looks good. 8j, 2j. Good. All right. So this is 2 plus 3j times minus 2j minus, and then it's going to be minus a negative 16j. And then on the denominators, minus 5 plus 12j equals. Now note, I'm leaving the denominators. I'm not doing any reductions, even if there are reductions there, because I know I'm going to get the same two denominators. And why do I want the same denominators? Because up here, when I subtract the two of them, I'm going to need a common denominator. So I'll have that common denominator already. First term, negative 4j. Second term, plus 6 plus 16j, all over minus 5 plus 12j equals 6 plus 12j divided by minus 5 plus 12j. Okay, so V phasor equals V1 minus V2 equals V1 minus 24 plus 12j. They both have the same denominator, so I'm just going to put them all over the common denominator. Minus 5 plus 12j. And then I have minus 6 plus 12j. So let's see what that's equal to. 12j minus 12j, wow, cancels. Minus 24 minus 6, very interesting. Minus 30 divided by minus 5 plus 12j. Equals. Well, actually not equals, let's multiply it by minus 5 minus 12j, minus 5 minus 12j, and let's see what we get here. In the numerator, all those negatives cancel, so I just end up with a 30 there. In the denominator, I'm gonna end up with 5 squared plus 12 squared. Just a reminder, 5 squared plus 12 squared. And that's gonna give me 169. And then I'm still multiplying that by 5 minus 12j. Now I'm ready to put this into its polar form because I want the answer in polar form. So 30 divided by 169 times square root of 5 squared plus 12 squared is going to be the square root of 169 at an angle, and I'm looking, these are both positives, excuse me. Let's get that cleaned up, and right there cleaned up. 5 plus 12j. This negative cancels with that one and that one. Gives me a positive 30. So the angle is tan inverse of imaginary over the real, 12 over 5. So now I want to convert that back to V. Therefore, a lot of people use equal signs. It's not equal. A phasor is not equal to a time domain voltage. Therefore, V equals 30 root 169 divided by 169. Now, I think we chose a cosine reference, and we had a cosine of AT, so it's going to be cosine of AT. I put all of that back in. Remember, that's what we didn't carry around. And all we put in is the amplitude and the phase shift. And that is a voltage that's in volts. Okay. So that completes our problem that we worked on last week, assuming I didn't make any math mistakes doing all of that work. And you never know, it's very easy to make math mistakes. We're not overly concerned about the math. We'll double and triple, quadruple check. By the way, one of these beauties in solving these problems, especially if you're doing them in homework, when you get to this point, you have your equations and you want to solve the problem, and you're left with a 2x2 or a 3x3. All you have to do is plug those numbers into MATLAB. Remember, MATLAB can handle complex numbers with no problem. Can handle complex numbers with no problem. So you can do that. You can get your answer to these values, the values for V1 and V2 directly through MATLAB if you want to. All right, any questions on that? Rushi, just an FYI, your quiz has not come through at all. So we're running out of time to have that quiz submitted via an email. All right, let's look at a situation where we've looked at superposition before. So let's give an example. We're going to give a trivial example. And when I say trivial, you'll see what I mean by trivial. So let's assume that we're given this circuit. Three ohms. Four. Let's make that a half a Henry. Three ohm resistor. Another half Henry. And then a voltage source. The voltage source, I'm going to make that 8 cosine of 2t. Okay, then in the middle here, let's get this capacitor in the middle. And the value of the capacitor is 1/9. Apologize for putting that short in there. So here's our circuit. And what we're going to do is we're going to find this steady state voltage V. When you look at this circuit, there should be some observation about something that bothers you a little bit, hopefully, at this point. What is it that bothers us a little bit? First of all, I do want you to note there are 3 storage elements in this circuit. That would be a third order differential equation if we wanted to take that approach. Good luck to you with that. I won't be doing that. Okay, what is it about this circuit that's different than what we've been doing in this world?
It has a current source and a voltage source.
Okay, and we can handle current and voltage sources, so that's not a big problem, but it's more than that with regard to the current source and the voltage source. What is it?
They're in different forms.
Different forms. Define they're in different forms.
So the other one has an omega equal to 2, the other one is just 4.
Okay, so I wish I had different colors for you. This is a DC source over here, which, by the way, is omega is equal to 0. Don't ever forget that. And this here is an AC source. So, because the sources are of different frequencies, they are different types, in order to solve this for just the steady state solution, we must use superposition. We're going to find the DC output due to just the DC source. We're going to find the AC output due to just the AC source. We must do that. It is critically important when you have two AC sources of different frequencies. Critically important that you do that. So for this one, this is an easier case. You love seeing these because we know one of these sources is going to be pretty easy. Which one's pretty easy to solve?
The AC source.
The AC source is easy to solve with phasors. What about the DC source? Can we just do a DC analysis of the circuit? Is that pretty easy?
Yeah.
And what will the capacitor look like at DC? What's the model for the capacitor for the DC source?
Open circuit,
Good. What's the model for the inductors?
short circuit.
Beautiful. So here we go. We're going to start by looking at the DC source. So this is due to the DC source. So I leave my source. And now I kill the other source and I model everything else with my models. Well, the model of a resistor is a resistor itself at DC. This will be V prime. Do not confuse that with the derivative. Everybody remember that? We call the first component V prime and then V double prime. This is not the derivative, not the derivative. That looks like a short. That looks like an open. 3 ohm resistor. That looks like a short. And what do I do? How do I kill this source? How do I kill a voltage source?
Take it out.
Okay, how do I take this one out? Replace it by what?
Open circuit.
Open or short?
Open.
Voltage source, 0 volts. 0 volts across an open, across a short.
Short.
Short is correct. So we replace it with a short circuit. We kill the source. Replace a voltage source by a short. Does everybody see how this really looks like the following? That's what we have. 3 and 3. So if that's the case, what is I? My current divider, it's the opposite resistor, divided by the sum of the two, times the resistor entering both. So there it is, 2 amps. Solve for V prime. V prime equals 3I equals 3 times 2 equals 6 volts. So there's our first component. Save that. Box it up. We need that. Okay, now what we're going to do is we're going to kill the DC source, and we're going to look at the output due to the AC source. And this is a requirement. We have to do it this way, unless we go the differential equation route. So anytime we're using phasors, we have to do this. There are other better methods, but they're cumbersome. Okay, so I'm going to draw the circuit. What do I do with the current source? I'm going to kill the current source. What am I going to do with that current source right there? I'm going to kill it. How do I kill a current source?
Replace it with its model and open.
Excellent. So we just open it up. That's the current source. Now all the rest. Here's a 3. This is V double prime plus minus. Here's my ½ Henry inductor. There's my 3 ohm resistor. There's my ½ Henry inductor. Here's my voltage source, plus minus. And then here's my capacitor in the middle. Okay, it's not DC, so the models we're using here are not the DC models. Let's get the value of the voltage source was 8 cosine of 2t. So let's put that in. 8 cosine of 2t. And this was a 1/9 Ferrocapacitor. Now what do I do? I'm solving for V double prime here. This is not the derivative, V double prime. It's the component of V due to the AC source, due to this source right over here. What do I do with this circuit? We want the steady state solution. What do I do?
Convert everything to the phasor model.
Outstanding. We'll go to phasor world. Here we go. 8, cosine reference I just chose. This is J1/2 times 2, which is J1. Is that correct? J1. This is J1/2 times 2. J1. Let me just go back up here. Yep. Okay. And then finally, this 1/9. Just a little scratch pad on the side over here, minus J over omega times C equals minus J over omega 2 C, the value of the capacitor, 1/9. So that is all going to be equal to minus J 9/2. Minus J 9/2. And yeah, they're ugly numbers, but that's okay. Don't worry about the ugly numbers. So here's what we can do. On this circuit, what I'm going to do is I'm going to perform nodal analysis. Let's call this voltage here V. This over here, by the way, is V double prime phasor. And here's my equation. I have V divided by 3 plus J. That's this current right here. Then I have plus V divided by minus J 9/2 plus V minus 8, because that's 8 right at that dot there, divided by J. Not too bad. Sum those up and they're equal to 0. And do a little cleanup here so you can see this. So this is going to be V over 3 plus J plus J 2/9 times V phasor minus J V phasor minus 8. Whenever you have these purely capacitors, purely inductors, we can always get the J out of the denominator. We can always do that. Okay, now I'm going to multiply by 3 plus J times 9. When I do, I get 9V, get my phase over there, 9V plus J2 times 3 plus J, all that times V, and then I have minus 9J times 3 plus J times V minus 8. And what you're going to feel a lot of times when you're working with these complex numbers is, oh my gosh, this is so messy. Just don't worry about it. Just deal with it. They're just complex numbers. All right, so let's get all of these values here. Just remember, this is...
That should be 3 plus J, not 3 plus 8, I think.
3 plus J right here. Thank you. It is indeed. Thanks, Jack. Okay, this term is when I multiply the J2 times the 3, that's 6J, and then J2 times J is minus 2, so just remember that. All of this out front is going to be 27j, and then it's going to be minus 9, and all of that has a minus in front of it. That minus sign in front of it. Okay, so let's group our j's. Here we go. 9 plus 6j plus minus 2 minus 27j plus 9, and all of those multiply v. And that is equal to, bring to the other side, I have a minus and a minus, that's a plus, and I bring to the other side, so it's going to bring this 8 times 9 minus 27j. And a couple steps there together. So this is just a number over here. In fact, I can factor that 9 out, and I get 8 times 9 is 72 times 1 minus 3j. Okay, on this side, let's group everything together. 9 plus 9 is 18, minus 2 is 16. 6j minus 27j is minus 21j. And yeah, I know they're ugly numbers. Whatever. Solving for v, v equals 72 times 1 minus 3j, all divided by 16 minus 21j. We would do this, 16 plus 21j over 16 plus 21j. And that's going to give us, here's my 72. In the denominator, I'm going to end up with 16 squared plus 21 squared. And then now I have to figure out what I get when I multiply these numerators. So let's see if we can get this carefully. 1 times 16 is 16 plus 21j minus 3j times 16 is minus 48j, and then I have minus 3 times 21 minus 63. J squared is positive plus positive 63. (72) over 16 squared plus 21 squared times, let's see what we have in parentheses here. So real numbers, 16 and 63. 79. 48 minus 21 is 27 minus 27j. And these are just numbers. Don't get caught up with the numbers. They're just numbers. Just numbers. Okay, that's V. Now, we want the phasor. So I can find V, if I know V right here, it's a voltage divider to find V phasor. It's going to be 3 over 3 plus j. Three over 3 plus j times V phasor equals 3 over 3 plus j times the following. And I know it's ugly. I'm not dealing with the ugliness. I'm just leaving it like that, multiplied by 79 minus 27j. Tell me what last two steps I need to take here. What are my two last steps?
Get 3.3 plus j out of the denominator.
Excellent. So I'm going to multiply by 3 minus j over 3 minus j. And so when I do that, it's going to give me this times this is 3 squared plus 1 squared. That's 10. This number I still haven't calculated yet, 16 squared plus 21 squared. It's just a real number. Just don't forget that. It's a real number. In the numerator, I have 3. I have 72. Those are all real numbers. And this product right there is where the imaginary part will come in. So there'll be a real part and an imaginary part. So let me do this. I'm going to pull up my calculator here and start to calculate. So we have, obviously, we have 79 times 3. That's going to give us 237. And then I have that minus 27. So 237 minus 27. That's the real part. For the imaginary part, I have minus 27 times 3. So that's minus 81, minus 81J. And then I have minus 79J. That's not too bad, actually, those numbers. Okay, all of this is a number up in front. Let me tell you what that number is. 3 times 72, that's pretty easy. That's 216. In the denominator, there's a 10, and then let's see, 16 squared. 16 squared plus 21 squared equals 697. So this is 10 times 697, all multiplied by 237 minus 27, 210. Minus 81, minus another 79, that's minus 160. See this 10 inside here? It cancels with that 10 in the denominator. So now all of this is equal to 216 over 697 times the square root of 21 squared minus plus 16 squared, not minus, at an angle tan inverse of minus 16 over 21. And 16 squared plus 21 squared is 697. I believe we calculated that before, right? That was 697, should be, equals 216 square root 697 divided by 697 at an angle tan inverse of negative 16 over 21. Last step for this. So therefore, V double prime equals, and I know it's ugly. When you get into the world of complex numbers, everything doesn't turn out to be 2, 3, and 4. Plug my cosine of 2t back in, plus tan inverse of 16 negative over 21. All right, are we done yet?
No, we need to add V prime.
Perfect. V equals V prime plus V double prime equals, I think we got, was it 6?
Yeah.
Thank you. 6 plus 216 root 697 over 697 cosine of 2t plus tan inverse of minus 16 over 21 volts. There it is. Now, if you thought this one was tough, I want you to think about what it's like if you have sources that are sinusoidal and have different frequencies. Because this first one was not sinusoidal. Look at how easy this DC analysis was right here. This DC analysis right there. This circuit, that DC analysis. Look at how easy it was. We were done in that much space. I'm going to remind you, That was the DC analysis. Look at the AC analysis. So if we have two sinusoidal sources or multiple sinusoidal sources with two different frequencies or three different frequencies or four different frequencies, we have to group all of the sources that are of the same frequency and find the output due to those sources of the same frequency. So however many different frequencies you have is the number of of circuit analyses you need to do. Everybody clear about that? Okay, so that was awesome. That was awesome. Let's do this. Let's pause for 5. Let's take 5 minutes and let's come back and let's see whether or not you want to take a look at 1 or 2 homework problems to help get you started this week. Okay, so let's take a 5-minute break. We will be back here in about 5 minutes. I'm just going to put the recording on pause and we'll see you back here in about 5. Okay, everybody back? So I'm going to go back to this circuits problem. I'm going to solve this problem that we had for our quiz. We'll do that. We'll talk briefly about the oral presentation that's coming up this week. We'll talk about Friday, the fact that we have no class on Friday. We'll make sure we cover that. We'll take a look at some homework problems before we move forward. So let's take a look at this circuit here. So V1 and V2 are 2 voltages. So equation for V2, we're going to write the 2 node voltages. Obviously, this here is our supernode. Because the supernode is connected to ground, we don't have to write an equation at that node. That's great. So all we need are 2 equations. So we'll start at V1. If we can, we want to use the voltages across the capacitors as our variables. And that's cool because V1 is the voltage at this node, V2 is the voltage at this node. So they are our node variables and they are the voltages across the capacitor. So it's ideal. That should make this a little bit easier. So starting here at this node, when I'm looking for this current, that's the current through the capacitor, it's CD VDT, but the voltage across the capacitor is V1. So that's 112 V1 prime. This current here is V1 minus VG over 6. And this current right here is V1 minus V2 over 4. Sum those up and they're equal to 0. A little cleanup by multiplying by 12. So we'll get V1 prime, and I'm going to group this all together, plus. So when I multiply by 12, this term here is going to leave me with 2 V1s, and this one's going to leave me with 3 V1s. It's going to give me 5 V1s. And then I'm going to write this negative, we're in, again, from here on the V2, I'm going to get negative 3 V2. And that's going to equal, I'm going to bring this term over to the other side of the equation, but don't forget this multiplies 12, so 12 divided by 6 is 2. It's going to be plus 2 VG. So there's our first equation. The second equation, I'll write it up here. So at V2, it's going to be very, very similar. So it's going to be 1/4 V2 prime plus V2 minus V1 over 4 plus V2 minus VG over 2. Sum those up and they're equal to 0. Take this one and multiply this one by 4. So when we do that, we end up with V2 prime by 4. I'm going to get 1 V2 there, and I'm going to get 2 more there. That's plus 3 V2. I'm going to get a negative 1 for V1, so it's minus V1. And for this VG, I'm going to bring it to the side. It's going to be a positive 2 VG. Okay, this is the one that looks like we're ready to roll because we almost have everything in terms of V2. That means this is the one that we want to substitute over here. So we're going to solve for V1. So when I do, I get V1 equals V2 prime plus 3 V2 minus 2 VG. And then I'm going to take its derivative because I need V1 and I need V1 prime. So V1 prime equals V2 double prime, there's my second derivative. 3V2 prime minus 2VG prime. So now I'm just going to take these two and I'm going to substitute into this equation. So V1 prime, let's put in there for V1 prime, it's V2 double prime plus 3V2 prime minus 2VG prime. That's that term. Plus 5V1. V1 is V2 prime plus 3V2 minus 2VG. And then it's minus 3V2 equals 2VG. We're almost there. We're almost scot-free. So V2 double prime, that's that term. 3V2 prime, 5V2 prime plus 8V2 prime. That term, that term. 15V2 minus 3V2, 15 minus 3, plus 12V2. Bring everything else to the other side. So I'm going to bring this to the other side. It's going to be plus 2VG prime. Here I have 10 VGs that I'm bringing over, plus 10. So 2 plus 10 is plus 12 VG. Here's the differential equation. I could have made you find the homogeneous response because it would have been easy, because V double prime plus 8V prime plus 12V factors very nicely when I look at the characteristic equation. But all I said is find the differential equation. That was the differential equation. Questions on that? Okay, if there are no questions on that, then let's just quickly talk about Friday. I think our registrar accidentally sent out an incorrect email about us being on spring break this week. We are not on spring break this week, but this week we do celebrate Good Friday. No class on Friday. So we have class today, class tomorrow, class on Thursday, no class on Friday. All right, so we will not be together on Friday, just tomorrow and Thursday after today. So that leaves one of those 2 days to do all presentations. What is your preference? I'm guessing it's Thursday.
Yeah, it's good for me.
Thursday's good for you, Jack?
Yeah, I'm good.
Good on that, Jordan? Misael, Connor, Thursday?
Yeah, that's good.
Good for Misael? Connor?
It works.
Okay, so listen, it's a brief presentation. We'll do it right at the beginning of class. So when class starts, we're just going to go through. I'll look for volunteers to go. If we don't get volunteers, I'll pull numbers out of a hat here or something to figure out who goes first, second, third, fourth, fifth, sixth, seventh, etc. Just a reminder to everybody. I know you don't need a reminder because you're all here every day, but this is part of the requirement to pass the course. Failure to write the paper, failure to do the oral presentation will result in a grade of F for the course. I think I would like to try to invite Dr. Rodriguez in so that I've got an outside person viewing the oral presentation. So how many of you have experienced or practiced with sharing your screen? Anybody? Does everybody know how to share your screen? So this is what I'm going to do right now. I'm going to stop sharing mine. Connor, I want you to go ahead and share your screen so I can make sure that, that everything works well when you share your screen. Beautiful. Okay. And so when you share your screen, there are a variety of things that you can do. One is you can share what you have on your computer. Two is you can share any application you're using on your computer. So when those windows are open and you share your screen, you get to choose among the things that you are sharing. So if you want to do a PowerPoint presentation, you can leave your camera on so we can always see your little icon from your camera. And then you can share your screen and you can pop up your PowerPoint if you want to. And then you can talk through your PowerPoint while you're doing that. Okay? Jack, go ahead and share your screen. Terrific. Beautiful. Excellent. And I'm seeing Google on your screen. Jordan, go ahead and share your screen. So far, no luck sharing your screen. Are you using a computer, Jordan? Go ahead and unmute and let us know if you're using a computer or a cell phone.
Yeah, I'm using a computer.
Using a computer? Okay, perfect. Just got your screen. I think, no, I didn't. Go ahead. There you go. That was it. Okay, perfect. Outstanding. Very nice. And so you're actually sharing the quiz that you had. See, so you can share anything that's open, any application that's open, you can share that. And then Sale, go ahead and share your screen. Perfect. Okay, so everybody knows how to share their screen. So you can utilize this if you would like to. I'm not requiring you to do this, but if you would like to, because there are things that some of you put some real nice pictures into your papers, go ahead and do that if you want to. So we'll do that first thing on Thursday. First thing on Thursday, a reminder, you are speaking to a technical audience. Even if we bring Dr. Rodriguez in, you're speaking to a technical audience. So we understand what voltages are, we understand what currents are, things of that nature. Okay, let's see, what else did I want to jump into? Your homework assignments. A couple of you sent me a few of them late, so I didn't get into the office and get them copied. So I've graded those. I've graded everything that you've submitted. I'm going to copy that and send that back to you. Jordan, when you sent me the second order differential circuits, what ended up coming back to me was the first order circuits that we had, not the second order circuits. So if you can just double check that, I think you may have sent a different homework assignment. Just double check that.
Okay.
All graded. I'll send those back to you so you can see what your grades are, so you know what your grades are on those. Okay. Any questions or comments? Okay. If not, it's your time to tell me what homework problem you want me to try to tackle. It's the free-for-all. Fight for it. See who comes in first.
27.
I heard 27.
Yeah, 27 was the one I was.
I hope it's not a hard one. Can you give me an easy one? Can you pick an easy one for me, please? I don't know if I can do 27. I don't even know what 27 is. All right, let me get the book. So for 27, oh yeah, 27 is an awesome one. I love that. Great question, because we didn't do anything like that in class, right? So we're looking at this impedance on 27. We're looking at the impedance, and what we're trying to do is we're trying to find out what frequency the impedance will be purely real. So just as an FYI, not that you all care, when that happens, we say that the circuit is in its resonant frequency. Okay, so there are certain things about resonant frequency that are really interesting. Sometimes they're real interesting. Sometimes they're slightly interesting. This one's just slightly interesting. So this is what we have for our circuits. This is number 27. So the circuit looks like the following. And that's 160 micro. Terrible author for giving us numbers like that. We're just going to deal with the numbers. 100 ohms, 25 nano. An author who doesn't know anything about working in industry, because you would never call a capacitor something in nanofarads. unless the world's changing and nobody told me. So A to B. So we're looking at ZAB, this impedance, looking in. ZAB. And so we want to know at what frequency will this look purely real? So first of all, what we have to do is we've got to convert this to the frequency domain. So when we convert to the frequency domain, this here is minus J over omega C, 25 nano. Ye dads. Ugly numbers. So, well, we can handle that. That's not too bad, right? We can look at least 1 over 25 nano. So what's 1 divided by 25 times 10 to the minus 9? Are we good at that kind of stuff, or are we not good at that? Not hearing the silence, the deafening silence. I'm thinking that maybe for now we'll just leave it at 25 nano, although we'll plug that in at the end. But 25 nano, 1 over 25 nano is 1 over 25 times 10 to the minus 9, which is 10 to the 9th divided by 25. You can take 100 out of that 10 to the 9th and get a 10 to the 7th and divide that by 25, that'll give us 4. So we can work this a number of different ways. But let's leave it like this. So that's that. Over here for this inductor, we have 160 micro is the inductor value, but this is J times omega times L times 160 micro. Okay, these two are in parallel. Let's call this Z1. See if you agree with the following. ZAB is equal to J omega times 160 micro, all plus Z1. You agree with that? Z1 is in series with that inductor. So just add those. Okay, well, let's see what the heck this is. This is J omega 160 micro times product over the sums. 100 minus J omega times 25 nano over the sum. 100 minus J 1 over omega 25 nano. Okay, so that here, that's our Z1 term. The first term will just hang around for a while. And I want you to note that the first term is purely imaginary. The second term, what we're going to do with the second term is first, I'm going to multiply just this second term. I'm going to multiply the numerator by omega 25 nano. And I'm going to multiply the denominator by omega 25 nano. And when I do that, I'm going to get, in the numerator, I'm going to get minus, yep, that was not cool. I don't know what I think it's like you double tap the screen or something and it shrinks down or blows up. So in the numerator, I have minus J 100. In the denominator, the first term is, I have this 100, and that's going to multiply omega. It's going to multiply 25 nano minus J. Okay, that's not so bad. That's not so bad. So you can see with this second term, in order to add these things together, we want this in a rectangular form. So I'm going to multiply by 100 omega times 25 nano plus J divided by 100 omega times 25 nano plus J. Okay, this is J omega, 160 micro. Notice that's just going to sit around for a while still. And now we have to multiply the numerators. Come on. So we're going to multiply the numerators. And then the denominator, we're going to get, so I'm going to write it out in front. Here's the denominator. 1 over 100 squared, omega squared, 25 nano squared plus 1. Yowie. Now, that multiplies. First, I have this times a plus J. That's going to give me 100 for the real part. For the imaginary part, I'm going to get minus J. And then I have 100 times 100. That's 100 squared times omega times 25 nano. Okay, we want this to be purely real. That means the imaginary part must be equal to 0. Well, here's the imaginary part. The imaginary part is this term, and then don't forget this is a multiplier times this term. So that needs to be 0. Okay, so what needs to be 0? So for this to be 0, J, actually, I don't even need the J in there, just look at the imaginary part. 160 micro times omega, that's that, must be equal to, because this is a negative over here, so the imaginary part needs to be equal to this, equal and opposite. But it's ugly, so it's 100 squared omega times 25 nano divided by 100 squared omega squared, wow, 25 nano squared plus 1. Now look at this, omega, omega. So we're going to multiply by the denominator, 160 micro times 100 squared, omega squared, 25 nano squared, plus 1 equals 100 squared times 25 nano. All right, here's what I'm going to do. I'm going to start solving for this. So I'm going to divide both sides by 160 micro. When I do that, I get 100 squared omega squared, actually 100 squared omega squared, 25 nano squared plus 1 equals 100 squared 25 nano divided by 160 micro. You can see how to solve this. It's just math. I know it's ugly math. So here's my 100 squared times 25 nano squared omega squared. Just to remind you what we have for the number out front. Oh, get this square out here, not in there. Equals 100 squared 25 nano divided by 160 micro minus 1. And now solving for omega squared, it's equal to 100 squared, 25 nano, 160 micro, minus 1, all divided by 100 squared, 25 nano, squared, and then we work all that mess out. And you can see that this is equal to if I've done the math correctly, you can see these numerator terms, parts of those can cancel. Okay, but this is all equal to a number. Everything here is a number. So I'm going to number crunch this in my calculator. And when I do, and you can do this, and hopefully I haven't made any mistakes, you'll end up with it's equal to the following. 300K all squared. So omega is equal to, and this will always be the case, plus or minus 300K. And the reason it works for the positive frequency as well as the negative frequency is because a positive frequency and the same frequency are the same thing. It's just one thing going in the forward direction, one thing spinning in the backwards direction. So if it's going to work for a positive frequency, it's going to work for the negative frequency as well. So we don't look at the positive and the negatives. We just say, don't worry about that. It's just 300K. 300K what? What are the units for omega? Radians per second. Okay. Then the part B to this was, well, what is the resistance equal to? What is ZAB when omega is equal to 300K? And the answer is, let's go back up here. It's this number times this number. Remember, this cancels with this. They cancel out. So it's going to be 100 over, I'll write it over here on the side. So ZAB, and it's obviously just a real number, 100 divided by 100 squared, omega squared, 25 nano squared, plus 1. And if I did all my math correct, if I remember correctly, this turns out to be 64 ohms. Let me just double check that. It is 64 ohms. If I did my math correctly. So it's a number crunch. What you're putting in here is when omega equals 300K. That's what you're putting in there, 300,000. Okay, questions on that problem? Okay, select another homework problem. I don't know, I either stunned you with all of that mathematics or you now no longer have any interest in all the problems because that was the one in the world.
70.
70, towards the end, huh? Okay, so 70 is an op-amp problem. I love op-amps, you probably know that, or maybe you don't know that. I love op-amps. I actually love op-amps for two reasons. One is students think they're hard. That's number one. Two is they're actually easy. And so I love op-amps because when students really figure out that they're easy, they love op-amp problems. Okay, so this is an op-amp circuit. A lot of cool things going on in this circuit. Again, it doesn't matter for us, with our analysis, it doesn't matter which is the positive, which is the negative terminal. But the negative terminal is clearly the one that has feedback. So we have this goes to ground. So we'll draw that to ground. Then off of here, there's a 200K resistor. And then there's a capacitor that goes to ground. And that capacitor is 100 picofarads. And this capacitor up top is 10 picofarads. And then from here, there's another element, right into this previous one, that is fed back. And so this element is a 100K resistor. Okay. And then we have a 5K resistor to the source. And oftentimes, these resistors are put in here to mimic it's the source resistance. It's not the source resistance. They didn't say it was, but oftentimes they put those in there for that reason. EG. It's ground. And this is going to be, oh, they actually gave us, which is interesting, they gave us a resistor here. It doesn't even matter. It doesn't even matter. It doesn't affect the circuit at all. So V0, 40K. We don't even use 40K at all in here anywhere. Okay, so what are we doing here for this? This is VG is 2 cosine 10 to the 6t. Find V out. And we're going to find V out. We're going to find the steady state response for V out. Steady state means great, use phasors. We don't need the transient response. That homogeneous response, we don't need it. Okay, so when we look at this circuit, we know never do mesh analysis on an op-amp circuit. So it's clearly nodal analysis. Start to put some nodes here. Let's call this V1. That's V out. That's VG right there. That is the same as this. And we know what that is. That's all ground. So this is 0 right there. Now we need to take this circuit and we need to do some converting. So I'm going to leave the conversions up to you because I know that you know how to convert these elements in the circuit. The resistors don't change. So this source just changes to VG, which is equal to 2 and negative 0. So this is 2. This here is 2. That's a phasor, purely real. Okay. 5K doesn't change. The 100 picofarad turns into minus J 10K. Minus J 10K. This one turns into minus J 100K, the other capacitor, minus J 100K. So just so we can see those, all the resistors are the same. This turns into V0, this is V0, this is V1, and now we're ready to roll. So we have this entire circuit there. We've converted it to the frequency domain, and we're ready to solve in the frequency domain for V0. So the way we're going to do that is I have 2 unknowns. I have V1, V0 are my unknowns, but I can't write a nodal equation at the output, so I'm going to write my nodal equation here and here. That's where the nodal equations come from. Let's start with the easy one. Let's do it at the inverting terminal. So at the negative terminal of the op-amp, this is the negative terminal of the op-amp right here. So we have this current, 0, and that one. That one's 0, obviously. So here we go, 0 minus V0 divided by minus J 100K plus 0 minus V1 divided by 200K equals 0. Started looking messy, but that one's not too bad. 200K, 200K.
Should be 20K.
Is that a 20K? All right, let's fix that. 20K, let's just check that. It is correct, it's 20K. So let's change that down here. Thank you for that correction. Okay, so common denominator is, don't worry about the J. We can get all of that taken care of. So let's multiply through by 100K. Okay, so this negative J is a positive J in the numerator. So I have minus from this minus, and then a positive J, 1 over J is minus J. And then I multiply by 100K, so I just have minus J V0. And then for this one, 100K divided by 20K is 5. So we're going to have minus 5 V1, and that's equal to 0. Box that up. That is a very nice, clean looking equation. So there's one equation. The other one is going to come from writing the equation at terminal V1. And there are a number of terms there. So I see 1, 2, 3, 4. So let's start. First one, V1 minus VG, but VG is 2, divided by 5K, plus V1 over minus J 10K. Some people would take this minus J 10K, they'd write the minus J as a positive J up in the numerator right here, right now. That's what a lot of people would do. I'm not a lot of people, I'm gonna leave it like that. Plus V1 minus 0 over 20K, plus V1 minus V out, and that's how V out gets into our equations. So V1 minus V out over 100K. Sum those up, they're equal to 0. I think if we multiply this one by 100K also, we'll be in very good shape. So when I multiply by 100K, I get 20 times V1 minus 2. Take the minus J, bring it to the top, it's a positive J, plus positive J, 100K divided by 10K, 10J V1. 100K divided by 20K is 5, plus 5 V1. 100K divided by 100K is 1, plus V1 minus V0 equals 0. Clean it up. So my V0 term, I have minus V0. Okay, now I add my terms for my V1, get the real part, 20, 25, 26. The imaginary part, 10J. That's it. 26 plus 10J V1 equals 0. There's another beautiful equation. So there's my two equations. Just going to write them one under the other so you can see them. Make sure my minus 5 V1 equals 0. And we're solving for V0. I'm going right for it with Kramer's rule. Denominator, minus 1, 26 plus J10, minus J, minus 5. Numerator, I substitute for the first numbers, and something's wrong. I got a 0 here. What did I miss? My mistake. See this 2, guys? I missed that. So over here, it's going to be 20. 20 times minus 2 is minus 40. Bring it to the other side. It's 40 over here. When we bring it over, it's 0 here, 40 down here. Sorry about that. So I have 40 and then 0. 26 plus J10 minus 5 equals 40 times minus 5, minus 200. And then minus 0. Ooh, that was nice. Divided by 1 minus 5, 5. 1 times 5, minus 1 times minus 5. And then minus, but with that minus j, it's going to be plus j 26 plus 10j. Okay, everything look good so far? All right, if that looks good, this is equal to minus 200 divided by, now this j times that gives me minus 10, so it's going to give me a minus 5 in the denominator. So I get minus 10 from these two, plus 5, minus 5, plus j 26. I don't like that denominator because I need to go back to polar form, so I'm going to multiply by minus 5 minus j 26. Minus 5 minus j 26. And so let's see what that's equal to. That's equal to minus 200 divided by 5 squared plus 26 squared. We'll get that number, don't worry about that. And then I'm going to take this negative, multiplying those negatives all makes it a positive, so I'm going to get rid of this negative on my 200. And so it's times 5 plus j 26. Now, here we go, the numbers. 200 divided by 5 squared plus 26 squared times the square root of 5 squared plus 26 squared at an angle tan inverse of 26 over 5. I think 5 squared plus 26 squared is 701 if you do that math. So this is going to be 200 divided by 701. In fact, let's make it just 200 root 701 divided by 701 at an angle tan inverse of 26 over 5. So therefore, V0 equals put my cosine back in. It was 10 to the 6t. Put all that back in and just pop the angle in there. It's a voltage, it's in volts. Now, what we would have to worry with a real op amp is whether or not any clipping occurs. Does this cosine get too large so that the op amp clips? We're not worried about that. I told you, I don't want to worry about that in this course. We'll worry about that when we're in the laboratory. But in this course, we're not going to worry about it in the lecture components. If I wanted to ensure that I didn't clip, what do I do? Any idea? If I want to make sure I'm not clipping. So if you look in the circuit in the textbook, this op amp has its rails, its power supplies plus or minus 10 volts. If I don't want to clip, I increase that. I increase it so that it is outside of the range of the cosine. So I just look at the amplitude of the cosine, because that tells me how high it goes and how low it goes. And I just make sure that I set my rails to be larger than that in both directions. Okay. We've got about 8 minutes. Anybody need a setup for another problem? Just get you started on another problem. Hearing nothing, it means either you're all great and you know how to solve all of them, or you don't need any hints.
Can we start on number 46?
46. Is that one of the Thevenin problems?
Yeah, it's the Norton equivalent one.
Yep, okay, good, very cool. So the Norton equivalent, 46. So this circuit, and you'll see this in the textbook a lot. This is one of the things I don't like about the textbook, believe it or not. I don't like about the textbook. This is already converted into the frequency domain. And it's unusual that somebody would convert a circuit into the frequency domain. If you're going to convert it for me, do the darn work. So I'm going to write this way. This is 0.4 plus 0.2J. I'm going to write it this way. 1/10. Actually, we could write 1/5. That would be smart. 1/5, 2 plus J. This is minus J20. And this is 40. And this is 20. And this is J16. So remember, whether you're finding the Norton equivalent or the Thevenin equivalent does not matter. It doesn't matter. So, because we know VThev equals, besides it's equal to V open circuit, it's equal to I Norton times Z Thev. So whichever of the two you want to solve, we can find this one, this one, this one. So take a look at this circuit. Let's play the same game we played before. Do you see any dependent sources?
No.
No dependent sources. So what do you think is going to be the easiest to find? VOC, I short circuit, or ZThev? It's ZThev. That's the easiest one to find. How do we find ZThev? We kill all of our sources, and then we look into terminals A and B and look at series parallel combinations. So when we look into the terminals A, B, this is what it's going to look like. 40. I drew this like a resistor. It's actually an inductor. But to us, it doesn't matter. As long as we have the value, J16, 20, and J20. Negative J20. I have killed the source. Open a current source. Killed it. So now what we have is these two are in series, and that's going to be 20 minus J20, and that's in parallel with 40. So 20 minus J20 in parallel with 40. I'll remind you, you can factor things out if you want to, but you'll see it when we do it. It's product over the sums, 20 minus J20 times 40 over 20 minus J20 plus 40. And that's equal to, well, in the numerator, let's at least factor out a 40. So it's a 40 times 20 minus J20. In the denominator, I have 20 and 40 is 60 minus J20. Now, let's divide top and bottom by 20. I get 40 times 1 minus J divided by 3 minus J. Okay, now that's not in the form we wanted because we're going to take that. So that was those in parallel, and they are then in series with J16. So ZAB is equal to this 40, 1 minus J over 3 minus J plus J16. So in order to add those, we need them both in purely rectangular form. So this is going to be 40 times 1 minus J over 3 minus j times 3 plus j, 3 plus j, plus j16. Clean up. Notice how all of our work, all of our tough work is always dealing with complex numbers. The denominator is 10. 40 divided by 10 is 4. Now it's 4. 1 minus j times 3 plus j. 1 times 3 is 3. Minus j times j is plus 1. 3 plus 1 is 4. Minus 3j plus a j, minus 2j, plus j16. This is equal to 16 minus j8 plus j16, which is equal to 16 plus j8. That's zthev. And that's a great form to put it in. So right now, when we draw our Thevenin equivalent, we're going to draw a Thevenin equivalent the following way. Actually, it's the Norton equivalent. So it's going to be I Norton, which is going to be I short circuit, but right now we'll call it I Norton. And then Z Thevenin plus J8. So now we have to find this. But the easiest thing to find is to find Z Thev. How are we going to find Z Thev? We're going to go back up here. Z Thev is if we analyze this circuit that we have right here, VOC. That will be VOC right there. So if we analyze that circuit, and I think the best way to do that is probably to use mesh analysis. We know what that current is. It's 1/5 times 2 plus j. This is, call that I1. And then VOC is going to be equal to I1 times 40 plus 1/5, 2 plus j times j16. Okay, that's this voltage plus that voltage. That's VOC. You can see that in that loop. That's VOC. So you're left with taking this circuit here, just working that and solving that circuit for I1. Once you have I1, you can then find VOC. Once you have VOC, now we go back down to here. Once you have VOC, I Norton is equal to VOC divided by Z Thev. Okay, so you're left with just solving for VOC to get that. Okay, that'll do it for today. That was a short lecture. It felt short and abbreviated because of the number of things going on there. So here's what we're going to do tomorrow. Tomorrow we're going to pick up and we're going to finish chapter 9. Chapter 9 has transformers in it. And in particular, they have the ideal transformer. They talk about the linear transformer and the ideal transformer. And I want to jump on that. I want to give you an opportunity to look at that. At least one of our projects was on a transformer. So we'll talk a little bit about transformers, how they work, why they work the way they do, what sorts of cool things there are. Mathematically, they're really, really interesting. And believe it or not, transformers, like op amps, when we put them in the circuit, they actually make solving the circuit easier, not harder. Seems like they're harder, but they're not. The concept of transformers has to do with mutual inductance. So I'm going to go back and do a kind of a re-review of mutual inductance and then kind of gloss over a lot of the physics behind it and hope that you've had it in your physics course. So we'll look more at the circuits part. If there are no questions, I'll just pause for any questions. Any other questions with regard to anything, presentations, direction we're heading?
Are you able to send me what I was supposed to turn in? Because I'm kind of confused on what I was supposed to turn in.
Okay, you're looking at you're looking at me now, right? You see me? No, let me
Yes.
here. You're seeing the small b. Okay. Hang on 1 second, Jordan. Can you see that sheet?
Okay, yeah, I'm sure that was what I turned in.
I got well, I'll double check, and I'll let you know. I'll send you an email right when we're done here. I'll double check, I'll send you an email. What I got
Okay,
printed off was the homework problems from the first order circuits. That's what I had. So maybe there was something else attached. Maybe I pulled up the wrong email. I'm not sure which one it is, but that's what I ended up printing off. So I'll double check that again. If you have it, you might want to just resend it if it's not a big deal.
okay.
Okay.
Yeah, I have it here. It's
Perfect.
just, I can just resend it
Yeah,
again.
go ahead and just do that then. All right. Okay.
All right.
Okay. Appreciate you all. Good chatting with you again today. Look forward to seeing you all tomorrow. Stay safe. Stay away. They're talking about this is a big week, big dangerous week this week. You've heard everything on the news. So heed the warnings and be smart. Okay. Take care. I'll see you tomorrow.